Okay, this is the Chapter 10 review. Chapter 10 was where we first hit circles, and so let's take a look at Section 10.1 on page 641. Primarily, it's just some terms to make sure that we know them. You can look through the vocabulary that's highlighted there. Make sure that you know what the terms are. Tangent and secant are the two biggest terms that we have here. And remember, if you have a circle, a tangent is just going to touch at one side, at one point. So this line up top, that's a tangent line, and here is the point of tangency. Let's call that point P. And then if we come from the center of the circle, let's say this is the center here, and we go to that point of tangency. All right, pretty close. The angle that's formed between the radius and the line itself is a right angle. And that's one of the theorems that we have here. If you have a segment drawn from the center, it's got to be coming from the center, so it can be a diameter or a radius. But if you're going through the center and you hit that point of tangency, that is going to be a right angle. The other theorem we had was if you have a circle and you take a point somewhere outside the circle, say this one over here, and you draw the two tangents. So here's one on top, just touching right there. And then here's one on the bottom, just touching right there. The two lengths from the point that's outside the circle to these 2 points of tangency, those are congruent always. So if you have tangent segments from an external point, those are always the same. Then in section 2 is where we first started looking at arc measures. Well, the first one that we took was if you have from the center, you take two radii, one here, and let's say that this angle between the two radii is 80 degrees. That means the measure of the arc over here, this arc, that's a part of a circle, not the whole thing, but just part. That's also 80 degrees, right? So that's the measure of the arc. In classifying arcs, we have three different types. We have an arc that's less than 90. If it's less than 90, it's a minor arc. And we use two letters to name it. So we could have arc AB. If you see just two letters with an arc over the top, you know it has to be less than 180, not 90. Less than 180. Change that. Now then, that's correct. It's less than 180. Or if it's equal to 180, then we have a semicircle. Well, a semicircle, you have to have three letters because you've got to be able to determine which side of the circle that you're going on. Let's say that we have a circle here, small one, and we have a diameter cutting this into two semicircles. And let's just put the endpoints, say X and Y, and let's call the center C. If you want to go on the semicircle that's on the left side, you've got to pick a point somewhere between them, and let's say that's W. Let's pick one over on the other side and label that V. So arc XWY lets you know, well, I'm starting at X, going through W, and ending at Y. It has to be the one on the left. If I say arc Y VX, well, that's going to be the other one, all right? So semicircles have to have three as well. And then finally, major arcs have three, and that's when you have greater than 180, less than 360, but that's a major arc. A major arc is also always identified with three letters. So if you've got three, you know it's at least 180, but it could be more, right? So here is circle, close enough, and let's put some points down. Here's A, B, and we'll put C over here. If I take the measure of arc A, B, C, right, that's the measure of arc AB. Well, AB looks to be a minor arc, so I'll just put that as 2 letters. But then we have to add to that the measure of this other arc, BC. And so we add that, and that's the measure of arc BC. So the 2 minor arcs are actually giving us a major arc. Anytime that happens, you've got to make sure that you label the major arc with all 3, because if you just say measure of arc AC, then that arc AC is starting at A and going the shortest distance to C around. And if you're talking about the sum, that's not the same one, right? And that was the arc addition postulate, which was also in there. Section 3, some properties of circles when we have segments involved. The first one, if you have 2 chords, so I put one across the top here and another one over here on the side. If these 2 chords have the same length, if they're the same length, then that means that the arcs that they cut off, starting at the same endpoints but now on the circle going around, the 2 arcs are congruent. They have to be the same. Another property, if you have 2 chords that are congruent, their distance from the center point is also the same. Well, distance is always perpendicular, so it's going to come to the midpoint, perpendicular here, perpendicular here. Those 2 segments in blue are congruent if it's coming from the center. If this were a better circle, they would look better like that, right? That's one of the theorems from this section. If you have a circle and you're coming from the center and you hit a chord, right? So it can be a radius or a diameter, but so long as you're coming from the center, and let me put a chord over here on the left from here to here. If you go perpendicular to that chord and you continue on through to the arc, well, this is bisecting the chord, but it also bisects the arc that's over here. So if you knew that this entire arc were, say, let's say 100 degrees for that, well then this would be 50 and this would also be 50. Why? Because you're coming from the center perpendicular to that chord. All right, and that's primarily everything that we had from that set. Let's go to section 4. Section 4 is on page 662. All right. Inscribed angles. This is where we have 2 lines intersect a circle, and their intersection is on the circle. So let's take a line here and a line here, right? The point where they intersect is on the circle. The relationship between this angle, let's say this is angle 1, and the arc that's intercepted. Well, remember, there's only one arc. We'll call it B for big arc. The measure of angle 1 is that arc divided by 2. So if you're given the arc, you take half of it. If you're given the angle, then you double it to get the arc measure. And that was primarily section 1. If you have another pair of lines and they come through and they intersect the same endpoints, that same arc, then angle 1, whatever that is, this angle will be the same because it's intercepting the same arc. So anytime that you have a vertex on a circle intercepting the same arc, then those angles would have to be the same, and you could have a whole bunch of them. Another property, if you have an inscribed polygon. Now, not every polygon can be inscribed. So I'm going to put one down here. This is not a regular, it's supposed to be right there. But it's inscribed. All of the vertices are on the circle. Well, if you take a look at these two angles here, these opposite angles are supplementary. But so are the other pair of opposite angles. These two in blue, these are supplementary. Why? Because they're in opposite angles of an inscribed polygon. The angle has to be inscribed. And that's only for quadrilaterals. Only for quadrilaterals where the opposites have to be supplementary. That was section 4. Section 5 is then some other relationships, but again, it's dealing with two lines intersecting. So I'll draw a circle here, not going through the center, but somewhere inside. Well, let's call this angle 1. Angle 1 is intercepting two arcs in front and back of it. This one in front appears to be bigger, so I'll label this as B. The one in back, I'm going to say, is smaller, but it doesn't matter. The measure of angle 1 is the average of the two arcs. Well, the average is B plus S divided by 2. Average, so if it's on either side, it doesn't matter. You're add those two together, divide by 2. The top of page 673 has a very good illustration of on the circle, inside, and outside. So let's take a look at outside. Outside the circle, we have two lines intersecting here and here. Well, here's the angle, angle 1. And now then, we know which arc is definitely biggest. It's the one furthest away. So this one we'll call the big one. And the one closer to it is definitely smaller. But when the vertex is outside, and this is outside the circle, the measure of that angle is the big one minus the small one divided by 2. So we've had 3. If you're on the circle, you've only got one arc. It's the arc divided by 2. If you're inside, it's the two arcs added together divided by 2. And if it's outside, like this case, it's the big arc minus the small arc divided by 2. You can also have some other setups. It doesn't just have to be 2 secants. You could have 2 tangents. So we looked at the lengths of the segments a while ago. They love little problems like this. Here's the 2 points of tangency. Well, you have 2 arcs. There's angle 1. The arc that's closest to you is the small arc. And I'll label that S. Then I'm switching colors to green because the arc that's far away now, it's the other part. And so this is the bigger arc. Well, it's still the same relationship, but sometimes they'll only give you one. Suppose they tell us that the measure of arc S is, I don't know, let's say it's 120 degrees. Just picking that. They'll ask for angle 1, and they won't give any other information because you can tell what the big arc is. These 2 arcs together have to add up to 360, so the big arc has got to be 240. Well, then, to solve for the measure of the angle, the measure of angle 1 is big minus small divided by 2. The big arc is 240. 240 minus 120 divided by 2. That's going to be 120 divided by 2, or 60 degrees. This would have to be 60 degrees. They can also just give you the angle measure and then ask for the 2 arcs, which is another possibility for these types of problems. You can have a secant and a tangent line. and then you have the two arcs. And that's with the angle measures. Now for the segment lengths with lines intersecting circles, I didn't use much of the textbook here. I told you to use mine. Vertex to circle times vertex to circle. Here are two lines intersecting, and they're intersecting inside. The vertex to circle on one segment, right, times the length on the other side, still on the same segment. So vertex to circle times vertex to circle. You got those two lengths on that one line are equal to, well, the length of the vertex to circle on the other line, and again, you've got two lengths there. So if you had something like this, let's say that this is 12 and this is 3 for the two segment lengths on the red cord that's there. And let's say that on the green, this one, the longer one, is 10. We'll call this one X. Well, again, start at the vertex and go to the circle. So 12 times 3 has got to equal the X times the 10. Well, multiplying this out, you get 36 is equal to 10X. Well, divide both sides by 10. X has got to be 3.6. And so that would be the value of X. This is where they intersect inside. Nobody has problems with inside because the lengths are always given that you're multiplying. The problem comes in when the two lines intersect somewhere outside the circle. Let me get this looking a little bit more like a circle there. Here is one segment. Here's another one, two secant segments. It's still the same property. Vertex to circle times vertex to circle is equal to vertex to circle times vertex to circle. But now, the vertex to circle, the first length that I'm going to take is all the way across to the far side of the circle. Right? There's two lengths from that vertex to the circle. I'm going to use that one first, and then I take the second one, which is the near side. So there's two different lengths, vertex to circle times vertex to circle. I've got to do the same thing on the other line. Go all the way across to the far side, because that's the length that people forget. And then for the second one, take it just to where it hits the circle, right? So we had lots of problems like this. If you have a tangent and a secant, remember the tangent is going to be the same length squared. So these two in red, say if we had come up here, we had a tangent, we would have to count whatever this length is, let's say X, twice. So you would have X squared is equal to, and then take the lengths on the green secant segment, whatever those are, the long one and the short one, getting to the circle. That covers everything in section 6. And then finally, section 7 was write and graph equations of circles. Main thing you have to remember here is the equation of a circle in a plane. All right, this is the general form, and that is x minus h quantity squared plus y minus k quantity squared is equal to r squared. The center of the circle is h, k. H right here is the x-coordinate of the center. The k is the y-coordinate of the center, right? These 2 points, h, k, they are not on the circle. They're the center of the circle. If you want to find points that are on the circle, you plug in something here for x or something here for a y. That would give you those, all right? And so the number that these are equal to, the r squared, that's always going to be the radius. So let's take a look at something like this. If you had x minus 3 squared plus y minus, plus 1 squared is equal to 49. It's going to ask, what is the center? Well, the center, you have to take the opposite of the number that's here because it's minus h. What are you subtracting from x? You're subtracting a 3. Well, over here for y, what are you subtracting to get positive 1? You're subtracting negative 1. It's the opposite of what's here. The radius is the square root of whatever this number is. It's not 49 for the radius. It's the square root of 49, which is 7. So you'll be given an equation of a circle just like this, and they'll say give the center and the radius. All you have to do is identify them. Or if they give you the center and the radius, the part in red, you've got to be able to go through and write the equation of the circle. You may have to graph it, all right? Put down the center point first, then go left, right, up, down, however many units that radius is, and that'll give you a quick graph of it. And I think that's most everything that we did in Chapter 7. Again, on page 697, you have some of those big ideas. Mostly it's the arc measures and how those are formed, how we get those measures with the angles when lines intersect, and then the arc length, the segment lengths when lines intersect circles. And that's the Chapter 10 review.